Perfect. I'll start now, Jeremy.
Go for it.
All right. G'day, everybody, and welcome to Builders Declare webinar number 11, Beyond Build Quality. My name is Hamish White, and I'm one of the founding members of Builders Declare and directors of Sanctum Homes, and I'll be your host for this evening. I'd like to begin by acknowledging the traditional owners of the land on which we meet today. I would also like to pay my respects to elders, past, present, and emerging. Today's webinar is called Beyond Build Quality and is part 2 in the series of what makes and breaks a high performance home. If you want to check out Jeremy's previous webinar, What Makes and Breaks a High Performance Home, be sure to join our YouTube channel. A little bit of an introduction in today's webinar. Whether it's a well-executed passive solar build, passive house construction, or just a well-built home, design and build quality are not enough to achieve a carbon zero outcome. Not even close. The technology we put into the house must be focused too. Must be a focus too. Sorry, Jeremy, I messed up your intro.
That makes sense.
Today's speaker, Jeremy Spencer, will tell you what you need to know to complete the job of a net zero outcome. This webinar is targeted to builders, architects, and anyone else wanting to know how to achieve a net carbon zero home so you can start designing, building, and living the low carbon future today. Our host for today is Jeremy Spencer and has been a registered builder, energy rater, and director at design and build company Positive Footprints for the past 20 years. Positive Footprints has won multiple awards for sustainability from both Master Builders Association and HIA and the National Sustainability Awards, for which he is now a judge. His company has worked to show that energy efficient, sustainable design and net zero homes are a cost-effective option and can be a mainstream reality. A previous GreenLiving lecturer and an educator in an early life, he is a strong believer that together we can bring about change in the way we build. Jeremy is one of the founding members of Builders Declare and currently sits on the Design Matters Board, the Sustainability TASC, and the NatHERS Stakeholder Consultative Group. Today's sponsor, a big shout out to today's webinar sponsor, which is Stiebel-Eltron. Stiebel-Eltron supply a range of great electric products, including instantaneous hot water systems, hot water and hydronic heating heat pumps, heat recovery ventilation systems, space heaters, and water filters. If you want to know more information about the products that Stiebel-Eltron supply, please check out their website, www.stiebel-eltron.com.au. Stiebel is spelled S-T-I-E-B-E-L. All right, let's kick off today's event. The information you're about to receive is based on the experience of the presenter and may not relate to your situation. If you'd like more specific advice, please get in touch with us via email. Jeremy's presentation will last for about 45 to 50 minutes, and then we'll have about 10 to 15 minutes to answer any of your questions at the end. Please be sure to place your questions in the Q&A box at the bottom of the screen and not in the chat box. So I'm going to throw it over to Jeremy to get things rolling. Thanks, Jeremy.
Okay, I shall attempt to share my screen. All right, you can see that, Hamish?
Yep, we're all good to go.
Beautiful. Oh, well, thanks for coming today, everyone, to this second part of what makes and what breaks a high performance home, beyond build quality. So for those of you who didn't see the last webinar, I was really just dealing there with the shell and the fabric and looking at the assumptions in the NatHERS House Energy Rating software that it assumes of the build quality, and then looking at how one can meet those assumptions with standard construction techniques so that you can make sure the house on the ground performs as per the star rating. This talk takes a similar a similar model to the last one, where I go through different areas of the energy use in a standard home and look at the low-hanging fruit to pick, and also look at pitfalls to try and avoid. It also uses this particular graph quite a lot throughout the presentation. I'm a Victorian builder. Victoria has the highest carbon intensity for our homes of any state. And so even if you're not from Victoria, this is actually a useful pie graph to look at and think about. Your pie graph from your state will be very similar, except in your state, in Victoria, we're very similar to Tasmania and the ACT in that we are heating for most of the year. So our space conditioning wedge tends to be very large compared to some of the warmer states. But the actual amount of energy that goes to our appliances, cooking, lighting, and water heating for the average home is pretty similar. So this should hopefully also be relevant to you if you're listening from other states. Just on this pie represents if you've got all the new homes, all the old homes, all the existing stock, and you averaged it all out and you see where the energy goes. This is the pie for the average house. The average house is about 200 square meters. In Victoria, most of the homes are dual fuel. So if you got the gas bill and the electrical bill together and you converted the megajoules to kilowatt hours and combined it with the electrical bill, you'd get an average of 52 kilowatt hours a day use. And of that energy use, that burning of fossil fuels to provide that energy creates 8.8 tonnes of carbon dioxide every year for the average home, with an average bill of 2,686. And as we go through this presentation and look at the pies, as you're playing along at home, I think it's sort of easy to think about this pie. If you quartered it, every time we save a quarter of the pie, that's roughly about 2 tonnes of carbon dioxide every year for the life of the house that you've saved. And also somewhere around about $600 you've saved for the homeowner. Okay, so this is where we finished the last webinar after looking at the build quality that we need to meet the house energy rating assumptions. So that if you get a 6-star home and you build it to those assumptions, you should save that much energy compared to the standard home. If it's a 7-star design and you build it to the assumptions, that's what you get for 7 stars. So you can see how the amount of space heating and cooling really goes, gets eaten away by good design with good build quality. So build quality is very, very important. 9-star and 10-star is a house that theoretically needs no mechanical heating and cooling. Of course, it is just theory because it doesn't look at extremes of temperature in the house energy rating software. But there's 2 things I'll say here. The first thing is that if you have a U-Butte passive solar or fantastic passive house design, and you can build it to this sort of standard and get this sort of performance, but if you don't also look at the technology that you put in it, you're going to find it very hard to get to a carbon zero outcome. And when I do judge housing competitions, I'm always very disappointed if I have a lovely design, but they've obviously put all of their thought and concentration onto the design and the build, and then haven't thought about what they're putting in the home and the effect of the energy from those choices on the house. Okay, so that's the first thing. The second thing is, if you, most builders don't get the option of doing a design build like I do, and so you'll just have to build whatever passes your desk, more or less. Now, if you have to build a 6-star home, I don't want you, there's no reason why that can't be a high-performing home as well. So don't think that, it's just going to be same old, same old. The technology is such these days that with wise choices, you can get a very low energy home and potentially a carbon negative home, carbon zero home, if you, choose the right appliances. So this whole presentation is actually a good news story for the building industry, and I hope some sort of roadmap, as I show here, to how our industry could become, one of the first in Australia to move to a low carbon economy. All right, so let's get into it. What is the first bit of technology? The first bit of important technology is heat pumps for space conditionings. In fact, heat pumps are going to be a bit of a theme. They are a game changer in our industry and should be used more. And, you know, you might be thinking, hang on, what is a heat pump? Here we have an air conditioner sitting up on the wall. An air conditioner is just another name for a heat pump. Some people call them split systems, heat shifters. They're all names for the same thing. They'll have an indoor unit and some sort of outdoor unit. Now, these, in the past, if I go back about 10 years or so, these would have been a big no-no to put in a sustainable building because air conditioners only ran at one flat speed and they used a lot of energy. And so you wouldn't want to put your name to a sustainable home and have, you know, air conditioners in it. That whole equation has turned and flipped completely on its head. They are no longer energy guzzling. They have inverter technology. They only heat as much as they need to keep up the temperature. In fact, there's a lot of technology. This is a Daikin US7, and I've put in quite a few of these particular models. These particular ones have a humidity sensor built into them, so no more of that dry nose that people have been, some people may not like air conditioners because they feel it dries them out. Well, now you can set the humidity on them. It can also, it's got a third pipe, so it can bring in fresh air. It filters that air. It cleans its own filters. It can be set to turn off when no one's in the room, so it can sense if you're in the room, and you can link it to a smart network if you want to. So very sophisticated technology, and I don't get any kickbacks for anything that I'm suggesting today. But why do we put it into, why am I suggesting it for a net zero home? The reason is that if I compare it with your standard, say an electric bar radiator or a gas wall heater, the most efficient that those things can ever be is 100%. If 100% of the energy that goes into the unit ends up as heat in your room, that's the most it can ever be. These things start off at about 300% efficient and go up to 600% efficient. Now, I know that sounds just completely bonkers, and it sounds like I'm breaking some rule of thermodynamics. So let's have a look at how they work. The reason they get these efficiencies is because they're not actually making heat. They are just shifting it from the outside to the inside when you're heating, and from the inside to the outside when you're cooling. And this is my idiot's guide, if you like, from an idiot on how they work, because they're actually reasonably complex machines. But inside, you'll see that there's a looper pipe that goes around in a squiggly fashion between the indoor unit here and the outdoor unit on the outside. There's two fans, and inside of that pipe is a refrigerant. And that refrigerant is just a gas. And the property of a gas is that if it expands, it gets cooler. And if it shrinks, if it gets compressed, it gets hotter. And you may have felt this yourself. If you go camping and you undo a gas cylinder or a gas cylinder on barbecue and you don't do it quick enough, you get that shoot of gas at you and it's really cold. That's because it's expanding out and so it feels cold. And you might have felt the other one if you're pumping up a bike tire with a hand pump. You'll notice that the end that you sort of squash the air at, that gets really hot. That's because you're compressing the air. And it just uses that principle. And so what happens here is the refrigerant comes through this expansion valve, expands, and it goes down to around about -40 degrees or so. Now, the air outside might be 0 degrees, might be -5, but compared to -40, that air is really warm. And the fan blows the air across the pipes here. The heat goes from the air into the refrigerant. It then goes around and it gets compressed through the compressor. And then all that heat gets squashed into a small space and the pipe becomes very hot. And it goes to the indoor unit. Now it's all very hot and condensed. And a fan blows across those hot pipes and blows heat into your room. In the process of blowing that heat into your room, it's also cooling down the refrigerant in the pipe, which then goes back out, gets expanded again, goes down to that -40-ish, and the process repeats. And so that's how it heats. In cooling mode, just runs exactly the opposite way and takes the heat from the inside, and dumps it onto the outside. Now, doing this is a really important thing to know about coefficient performance, because this is what you're looking at. A coefficient of performance is simply a ratio of how much energy it uses to how much heat it shifts. So if it uses 1 kilowatt hour of energy to run for an hour to pump this refrigerant around, and it shifts 3 kilowatt hours of heat from the outside air into your house, that's a COP, or a coefficient of performance, of 3. If it shifts 4 kilowatt hours of heat, that's 4. If it shifts 5, that's 5. And the best are almost at 6 kilowatt hours of heat being shifted for every kilowatt hour of electricity used. So absolutely magical, amazing machines. The EER, the energy efficiency ratio, that is exactly the same number, but that's just when it's in cooling mode, to tell you how efficient your cooling mode is there. If you want to know more, go to this, the engineering mindset. That's where I got this information from. Okay, now what you just saw then was what they call a single split system. That's where you've got one head on the outside and you've got a motor, sorry, one motor on the outside and one head unit on the inside. But you can link multiple head units on the inside to one larger motor. One thing to know about doing this process though is that for some reason, I'm not quite sure of the engineering behind it, the bigger the compressor size, this is sometimes known as a compressor, this motor, the bigger the compressor size, the less energy efficient it is. It goes down a little bit, not too much, but a little bit. So the most efficient thing you can do is do a lot of single split units, but sometimes space is at a premium. And so we just put on the one motor and link it to multiple heads. Now I know also some people don't like to see, they want to go more of a slim line, a clean line look, and they don't want things hanging on their walls. Well, you can have ceiling units that go into the ceiling. You can also have units that you build into bulkheads, and they'll have just a vent grill over the front, and it'll look exactly like a ducted system. You can also have radiators. You can even put in, if you want to have ducted air still, no need for it, but you can still put in a ducted air system if you want, run by a reverse cycle air conditioner that makes the heating and the cooling. The efficiency of this will be down though, just because it has the inherent problem of ducting through an attic space where it's cold, losing heat out of that duct. And also, if you did see the last webinar, you'll know that part of the tightness membrane of standard construction is the plaster. That's what you've got to use to stop unwanted heat flow. And if you're cutting in vent holes for all of your ducts everywhere, it's very hard for that to be a nice tight building fabric. If you do want to know how to get these a bit more efficient though, I would check out this YouTube clip by Efficiency Matrix. If you haven't checked out their YouTube channel, they do some fantastic stuff on building tight. This particular one is all about the return air grill, which is notoriously leaky in a house. You can also do hydronic units. Not a great picture of that particular hydronic unit, but we did this house a little while ago now. But the boiler on the outside is no longer gas. We used a heat pump boiler, a coefficient performance of 4.2 from memory. So that's another option. You can also run it in the floor if you want to go that way. Okay, what to look for. So when you get a quote, what you want to do is you want to check out the specification document to see how efficient the unit that's been quoted is. So when you get a specification document, it'll look a bit like this. There will be a code for the indoor unit, a code for the outdoor unit, and this one is a 2.5 kilowatt system. The codes usually reflect the cooling efficiency or the cooling capacity rather than the heating capacity. So you get a heating capacity and cooling capacity. Usually heating capacity is higher on the same unit than the cooling capacity. So a 2.5 kilowatt system, typically you'd use that in the bedroom. The 3.5 may be a bigger room or study, and the 5 is probably some sort of open plan room, and larger. It goes up from there depending on the size of the space. But the number that you want to look at here, you want to go down to this EER, energy efficiency ratio, or COP. Because we're in Southern Australia, we're heating for most of the year, the COP is the one that's the more important. And here, this is that date in US 7, best in class, at least as far as I know at the moment. It has a COP of 5.81, like I said, approaching 6. The other thing that's good to bear in mind is the size dimensions. So here's the indoor size and the size of the motor on the outside. And it's good just to check that they're actually going to fit in the spaces that you want them to fit. The refrigerant is really important, and the next slide I'll talk about that. And this maximum pipe length, because they're a split system, you want to make sure that if you're specifying them or if you're designing them, that they will reach, like the pipe between them will reach. And if 10 meters isn't enough in your situation, you need to go to a different model that has a longer maximum pipe length. Okay, check the refrigerant type because of its global warming potential. We did a post about this, but it's worth going over again just to really drive it home for those who haven't seen the post. So unfortunately, the refrigerants that make these systems work and make them so amazing are themselves potent greenhouse gases. In fact, much more potent than carbon dioxide. This one here is best of class for an air-to-air heat pump. And it uses this R32 hydrofluorocarbon, and molecule per molecule, it's 670 times worse or more potent as a greenhouse gas than carbon dioxide. Now, the average air conditioner motor will have about a kilogram of refrigerant in it. Now, at end of life, if that refrigerant goes to atmosphere, that would be equivalent to, if it was R32, 675 kilograms of CO2 going to atmosphere. But that's best of class. The average, or the usual one being used in Australia is this R410A, and that would be equivalent to 2 tons going to atmosphere. So if you are doing renovations or demolitions where you're getting rid of the old reverse cycle air conditioners, they must be decommissioned by a registered plumber, and they will take up that refrigerant and they'll bottle it and send it off for reprocessing and reuse. Now, from now on, we're actually including this in our handover manual too. The owners should really know this stuff. The other thing, if you haven't used these before, is to know that they'll all have a drip pipe, a condensate pipe. And that isn't pumped, so it has to run on grade and it discharges by gravity. So you have to make sure that you never go uphill with that pipe, or else it will block the unit. It can run down like this, out onto surface, make sure it's grading away from the house. It's probably better and neater, instead of having a wet little trickle on the outside of your house, to run that into stormwater. If you're on the upstairs, this is not a bad way to do it, is to run that condensate pipe into the gutter. And this is from the VBA, you're allowed to do all of this. You can also tap them into downpipes, as long as it's not a charged downpipe taking water to your water tank. And I've also done this a couple of times if, because of the structure of the house on an internal room, you just can't get that condensate pipe to the outside of the house on grade, you can potentially run it to an internal wet area and put a ton dish like this in underneath a basin and have the condensate line come out in the bottom of a vanity and then into that ton dish. Also remember, again, if you haven't installed these, that each time you put a motor on, each one of these motors has its own dedicated circuit that has to go back to the board. So just make sure that that gets roughed in. It's hard to do it later. And lately I've become very aware of this, mind the gap. So all of the motor units have to have at least 150 mil gap behind them so that the air for the fan can come in and that it can run efficiently. Now that's fine when you've got a utility area like this at Hillside Home, where it's been created for the purpose. But often these things are on a blind side of a house and you've only got a meter down on that blindside access way. So owners will be able to walk past, but let them know you wouldn't be able to get a wheelie bin past typically, nor a wheelbarrow. So anyway, just things I've learned from hard experience there. All right, now this is a real pitfall, I think, of the whole system. And this is when the pipes come through we very often will get a big hole cut in like this. This happens, and it's typically, this is a standard installation. It's not a bad installation. That's because these pipes are not particularly bendy, at least on some models, not particularly bendy. And if it's come down through the stud work, it needs quite a big turning circle to get out. And so they have to cut these holes to actually fiddle with their pipes and get it working. If it is a back-to-back, if it is an external wall and you've got the motor directly on the outside of the wall, yes, you should be able to go through straight and with a much smaller hole than that. So what to do about this? Because this is just a terrible thing for your air tightness test when you do it. And also, more to the point, when you're trying to heat the home, you'll be getting cold air potentially coming in the back of the very unit that's trying to heat. And likewise, when you're trying to cool the home, you'll be getting hot potential air blowing out around the unit as it's trying to cool. What do we do about it? So this is a hard one, and if anyone's got better ideas, let me know. But what we do is we stuff this with insulation bats just around here so that it makes it hard for air to flow. And then we get one of these kinetic plates. And the unit, you see, gets put up on the wall, and the very last thing, you can't sort of gap it until it's up on the wall, and then it can tilt out once it's up on its hanger on the wall, and we cut a little hole in one of these kinetic plates, and we sort of slide it up and fiddle it in and get it reasonably tight around the pipe. It's not a perfect solution. It won't give you complete no air ventilation seal. It's more like the sort of hole that you get for your standard PowerPoint when they do the air tightness test. But it's a lot better than it would be if it was a big square hole. If you've got better ideas, let me know. I really think that the manufacturers themselves should come out with a better way of doing this. Okay, so so here's our builder, 6-star builder, but he's put in air conditioning, and some rooms have COP of 4, the main area maybe closer to COP of 3. So he's able to achieve, let's say, an average COP of just over 3. What that means is that he can provide this much heating and cooling of this wedge that he's got left after he's built his house really well. He can provide it with about 1/3 of the energy if it's a COP of 3. So wacko, there's a third gone. You can straight away see the huge part that this technology can play for the building industry. Now, of course, as COP of 4, it would be even more. Oops, that just went the wrong way, didn't it? COP of 4 and COP of 5, there we go. But let's say we're back at an average coefficient performance of 3, which is probably more of what you'd get in reality over the whole house, because like I said, the higher COPs are really only the smaller units, which are good for single rooms, and then they go down a bit. But that's the sort of performance that you would expect. So tick, we've done the air conditioning here. The next wedge here is for your hot water, and there are 2 strategies here. The first strategy is to limit the amount of hot water that you need. So this is an easy thing to do, so I won't spend too long on it, but simply going from a 3-star shower head to a 4-star, which is 7.5 litres per minute shower head, and you save about 15% of that hot water, of your hot water needs on your house. There is a slight pitfall to this though, and that is that it's no good just putting in a shower that gives you a poor shower at 7.5 litres. You need a shower that's been designed for low flow. Now, we've used a lot of these Methven Satin jets, so I'm perfectly comfortable with those, and we're actually trying one of their Aura jets now. I haven't tried it yet, but it's got a good report and looks pretty funky. So that's all I'll say about that. But go for a 4-star shower and you can cut your hot water needs a little bit. The other thing, so the shower use half your hot water goes to shower, and 1/3 of your hot water goes to your washing machine, typically in a home. So that's the other one to focus on. There's really 2 parts to focus on there, shower and washing machine. And later on, I'll go over how one might encourage the owners to go more efficient on their appliances. But if you do, you could expect to see about a 15% saving in that hot water wedge from the washing machine. So you do both of those things together, shower, washing machine, and you've cut down the actual hot water that you need by about 30%. Okay, the next step is to use an efficient hot water system. And lo and behold, it looks like a heat pump again. Yes, it is. So same deal, heat pumps can make hot water just like they can make hot air. Choose a heat pump with a COP of 3.5 plus. That's realistic for a hot water system. Look for systems that can be set to heat during daylight hours, and that will become more apparent when we look at photovoltaics in a minute, as to you're going to be making heaps of power in the middle of the day. So if you can get a system that works with that, you get that synergy of technologies that make things very efficient. And again, check refrigerants. Now, I do want to point out here lagging, because hot water pipes can get very hot. In fact, inside of this thing, it can get up to 100 degrees or thereabouts. That's why it's got a pressure relief valve here. If it gets too much pressure inside, it will let some of the water out to reduce that pressure. Now, this is a really nicely lagged job, and thank you, Brian from iSmart, for sending this through. Good job. Especially impressed with how neatly it goes through the cladding there. And I bet my bottom dollar that on the other side of that cladding, he has taped the membrane around the pipe, so there is no air penetration, and he's put the insulation nice and tight around that pipe on the inside as well. Watch out for that with standard builds. Plumbers are notorious for just putting through pipes and not thinking the broader picture about insulation. If there are plumbers watching, forgive me, I know you're amazing too. But really everyone on site needs to check for penetrations through the fabric. One thing that I will point out here, in fact, two things. One is the insulation on the valves themselves. They get really hot if you put your hands on them. That's great. You can get them pre-insulated like that. If you've got one that is just showing the metal, you can get these things called valve cozies. I know Renew used to sell them that will go over and protect that. And I'm particularly impressed, Brian, with this particular lagging down the overflow relief pipe. This is almost always left off completely, but don't forget copper is extremely conductive. And when that pipe is getting cold at night, it'll just be sucking heat out of this tank. So that also really should be lagged. So well done there. The rules on lagging. This is another little bugbear of mine, so I'll just quickly point out. If you look at the plumbing code, AS 3500, it will have a little map of Australia and will have zones A, B, and C. Melbourne is in zone B. Most of the capital cities, actually, there's a bit of A that goes down to protect Perth and Sydney, and down Tasmania, they're either in B or C. But if we look over at climate zone B over here, you'll see it says that pipes on the external house should be lagged with R0.6. And it goes down here, R0.6 is 25 millimeter diameter. Well, 25 millimeter thick, sorry, of the polymer around the pipe, 25 mil each side. So check that. I have a feeling that most people only put on the 13 mil. And even if you're in other states, it's not a bad thing to upsize from this, which is the bare minimum. And lastly, make sure it's UV stable, or else in 12 months or so, the UV will get to it and it'll start falling off. All right, you do those things for the water heating. And once again, if this unit has a COP of 3, then effectively you can produce this much heat with a third of the energy. Wacko. If it has a COP of 4, bam. So you can see how heat pumps are really just eating away at the energy use on this pie. Lighting is the next one. And the simple solution here is LEDs. I've shown this picture before, but just beware, this is really the only pitfall. These may all be LEDs, but if you put a lot of downlights in, remember, plaster is your tightest membrane on standard construction. It will be very hard to make this place work thermally at all with this many lights in. If you are putting in downlights as well, make sure they're ICF rated so the insulation can be run at least over the top. So at least it's insulated. Otherwise, you have to pull back the insulation on the ceiling side as well as having holes in plaster. This sort of thing where lights hang down into rooms will have much smaller holes in your plaster and it will be a lot cheaper for the electrician to wire. And if you do that, you should be able to save around about 30% compared to the average home on lighting. And cooking. Cooking's another easy one. There's only one piece of technology that's really changed in the energy efficiency space, and that's the induction cooktop. So the induction cooktop, 50% more efficient than gas, primarily because you don't lose gas around the side of your pans and your pots. Also, they perform extremely quickly, similar to gas. You know, you turn the knob and you'll get instant performance, similar to gas. And I actually went out to our Facebook group. Yes, we have a Facebook group, everyone. I suggest you, if you have any questions, that's where you should go. And the feedback on people who use these was amazing. Everyone was raving about them. So not only do they look fantastic and easy to clean and more energy efficient, but they also work really well. Now, they don't use a huge amount of power either way. You save a little bit using this, but the main thing that I like with this is that the cooktop is often, once we've gone through this process, is often the last gas appliance in the house. And if you get rid of a gas cooktop and change for an induction, you can abolish the gas meter and effectively save your $300 a year or so of just having that meter on site. So that's for the life of the house too. So that makes a lot of financial sense. The things that I will say, some tips. This is more tips really than pitfalls, but some of the induction cooktops have different amounts of ampage that they need for their power supply. So the normal one that we'd be running for a gas cooktop is a 10 amp cable up there, but it might require a 20 amp or a 32 amp, or a big one might even require 42 amps. So you need to know that early. So you need to know the model at rough-in stage, builders. You need to get the model information from the owner so that you can rough in the correct thing. It's too late to rough it in once all the plaster's up. The other thing to bear in mind is that once you have heat pumps for space heating, hot water system, and you've got an induction cooktop, unless you've got a very small house, there's a very good chance that you'll need to upgrade from single phase power to 3-phase power. This actually, even though it's a little bit more expensive, it's sort of offset by the fact you don't now have to plumb a copper pipe all the way to the cooktop. And it becomes a very good thing later when we're looking at how much PV you can put on. So if you do put on an induction cooktop, you can expect to save again out of this little wedge about a third of it. There we go. You don't save more because there's obviously other things that use energy in the kitchen, ovens and microwaves and so forth. All right, this last section, there's a little bit of a, well, I wouldn't say contentious, but it's often left alone and it's in the realms of the owner to work out their appliances, as it should be. But builders have a unique position during the build as experts on the build. And in fact, designers have the same sort of expert status during the design process. And often owners will be coming to me asking for suggestions, or what do I think of this appliance and that appliance? It doesn't hurt at that stage to give them some energy efficient versions that you would recommend. So if I break down this wedge here and we have a little bit of look and I turn that wedge into its own little pie graph, you can see how the appliances break down. And we've also posted this at Builders Declare, but it's worth looking at again. The big energy user here is fridge, because it's on 24 hours a day, 7 days a week, 365 days a year. So that's a good one to get right and get efficient. TVs are reasonably big as well. That's a good one to get right. Pools, if you're having a pool, definitely look at the pumps. And if that's a heated pool, even more energy will be used. And freezers, dishwashers, clothes washers, all your white goods together also make up a reasonable chunk of your appliance energy use. The miscellaneous, that's just things that get plugged in over time, and home entertainment and consoles and things, that I do think is in the too hard basket. But sorry about this. I assume everyone can still hear me. What do you do now that you know this? Okay. So this is what I do, just as a way of communicating some ideas of things to look for the clients. I make a list of all those appliances, and I put down the brand and the model, a description of them, and I put down what the rating is of them as well. So let's have a look. And then I give this to the clients, and this is my suggestion. So for instance, the fridge, this is a high sense, and that's the code. 6 out of 10 stars, Australia's highest ranking fridge. Or dishwasher, 5 stars out of 6. And 5.5 stars out of 6 for water rating as well. So I say what the rating is and also what it sort of goes up to. And that gives clients an idea that when they go shopping, well, they'll check these things out. They'll either choose, usually they choose sort of half the things I recommend anyway. And if not, they tend to choose something around that in efficiency. They know that, I've chosen something very efficient. They probably don't want to disappoint me too much. And they come back with something in the ballpark. So anyway, that's what I would suggest you do there, is make your own little table of suggestions. A good place to get the information to fill out that table is www.energyrating.gov.au. They run this whole star rating thing, which is quite a robust system, and all of your white goods are represented there. You go to that website, click on search registration database. You can choose a product. In this case, I've chosen a fridge freezer, and then you can just press rank them by star rating. There's 233 in this particular search. And that's where I got that high sense from. I then did a product review online, saw what people thought of it. People liked it, let's put it in. Another place to get really good information is the Choice magazine. It's a reasonably cheap subscription, goes for a year, and they keep updating you with what is a good appliance and what isn't a good appliance. So that's always a good one to fall back on. And of course, Builders Declare have their own socials and provide plenty of information. But if you're asking after a specific question, if you're not already, go to the Builders Declare Facebook groups page. I'm trying to grow this thing as a hub where builders can come and they can share information with other sustainable builders, trying to create a Sustainable Builders Alliance. So if you want to be part of that, come to that page. So just with a little bit of information, clients very often take some on board. If they don't, they don't, but it is such a simple thing to give some information. And if they do go for higher star appliances, the sort of saving that you'd expect is somewhere between 30 or 40%. And so look at what we've done to this pie here. We've really decimated the thing. We've probably saved around about 2/3 of the pie just through efficiency. So well done if you've got this far. The next step is to use photovoltaics typically to offset it. This is the next step of the puzzle on the roadmap. All right, so this here was this is the first house back in 2012 that my client sent me his bill, or in credit. They had a 3.5 kilowatt system, and they were in credit for $454 back in the heyday of the 60 cent rebate per kilowatt. Now, back then we were specifying a lot of gas. So we had gas hydronics and gas cooktop and gas, solar gas hot water. So I don't exactly know whether this house was 100% carbon zero, but I'm sure it was sort of in the ballpark. That is giving out enough electricity to offset its energy use in the realm of gas there. More recently, this is a house that we built a bit over 2 years ago. So I've got 2 years of data. This house is 100% electric, 4.8 kilowatt system. It only draws 0.6 of a kilowatt per day as a net result. Obviously, it's drawing more at night, and during the winter, it will draw more, but during summer, it will output a lot more. So the net balance is approaching zero there. And this is a renovation that we did that has a similar, this one's 3.3 kilowatt hours a day with a 4.7 kilowatt system. Didn't even have a north roof on this one because of the way the block was shaped, but does have east and west, but still getting very good net sort of outcomes there. So I just show those just to show you that it's really possible for the building industry to move to a much lower carbon intensity. Not particularly difficult, I don't believe. And that brings me to my PV system sizing rule of thumb little diagram here. Now, this is just a ballparking exercise, so don't go writing me letters if it doesn't work for you. However, I find it it's pretty accurate in predicting for myself what sort of system size we should be going for to break even. And the way I'll explain this thing is just by doing a demonstration. That's probably the easiest. So let's just say I'm a builder, I've got a house design and 6.7 stars. I've watched the first video in this series or first webinar in this series, and I've built the house, no thermal breaks, did the installation properly. It's nice and tight, put in the correct windows, and I should be able to see that 6-point-star rating in the amount of or the less heating and cooling it would need by about that much. So there we go, 6.7. So you can see the little star marks here. So whatever your house design is, if you think you built it to the right standard, you can start dialing up or taking away some of this pie. This is how this particular thing works. So now here we are at 6.7 stars. Now on this build, the builder is also able to put in reverse cycle air conditioning throughout, an average coefficient performance of 3. So effectively, he can provide this much space heating and cooling with about 1/3 of the power. So we just rub out 2/3 there. Okay, on water heating, he was able to convince the clients to put in a 4-star shower head, but they had an old washing machine that they wanted to bring from an older house and reuse. So he can maybe get 15, half of that little pie. See this black line? That's my 30% saving for 15% of shower and 15% there for a washing machine. But my builder here, he was able to go and get a Stiebel Eltron heat pump hot water system, and effectively that's got a coefficient performance approaching 4. So he was able to provide this much hot water with about a bit under 1/4 of the energy. Lighting, we put in LEDs, or he put in LEDs. So he was able to grab that little bit. Cooking, couldn't convince the owners to go away from gas. They like gas. And they had their own appliances. Okay, so that's the job. The next step in doing this is to bunch all of these wedges together. And now all you do is you just start reading around in a clockwise direction. It's 2 kilowatt panel system, 4 kilowatt panel system, 5 will be in there somewhere. So somewhere around 5.5 on this particular example. This house should start breaking even as long as it's been built properly to perform as per the star rating, and it's had these efficient heating appliances and things, energy prevention measures used on the house. Now, the next thing to do on this bit of thing is to back yourself a little bit or cover a little bit of risk and just the vagaries of real world application, and to round up. So round up to 6 kilowatt panel. So that's probably where I'd be starting the conversation with owners and say, put on 6 kilowatts. Having said that, I did, one of my solar installers did contact me in the week, and he said, Jeremy, I hope you're just going to tell them to put on as much solar as they can. And there's a real point to that, because solar power and making your own power just has so many uses and applications in the house. So it does make sense to put on pretty much as you can. However, this is the way this works. Now, there's two more provisos to this. This works for the average 200 square metre house. If you've got a bigger house, I'd add 2 kilowatts of panel for every 100 square metres that you add. If you add 50 square metres, maybe just 1 more kilowatt of panel. And for a 2 kilowatt, also add if you have more than 3 bedrooms, which is the average house has 3 bedrooms. If you have more than that, add another 2 kilowatts, because the potential of more people to be living in that house over time exists. And you can also use this little thing to work out how much panel size that needs on your roof as well. I can see I'm starting to approach time, Hamish, so I'm going to start wrapping it up shortly. All right, I'll avoid which panels and which inverters to choose, only to say solar quotes. I have no affiliation with any of these panels, and I'm not an expert, though I've used a lot of these things before. But I found that this channel on YouTube has pretty good information. But watch it, make your own choices. I've used the Fronius, these inverters, Fronius, SMA, SolarEdge. I found them all pretty good. But the important thing that Mr. Solar Quote says is try and get this 10-year warranty. Go for a 10-year warranty. Some of them will already come with a 10-year warranty. This is, we're talking about inverters now. Sorry, I skipped ahead a little bit. So we're talking about the inverters and the solar panels. Try and get a system that has a 10-year warranty to it. Sometimes it'll only be a 5-year warranty, and you can pay a little bit more to upgrade to that 10-year. One of the pitfalls that I'd say if you haven't put on solar panels before is just watch out for overshadowing. If you do have overshadowing, if you choose the wrong sort, what can happen is that this could be what they call a string setup. These could all be linked in series, and if one of the panels goes down because of shade, the whole string goes down to that level of output. So if shade is an issue for you, the solution, instead of getting a string inverter, talk to your installer, discuss microinverters. They sit on the back of each panel, and they basically regulate it so that the one in shade will drop in output, but the others won't. Another little tip is don't install inverters in a sunny position. If they get hot, they don't work as well, and it will probably reduce the life of the inverter. A couple of quick tips. If you are installing on a tile roof, you may find it difficult to find contractors because tiles break easily. Make sure you've got a lot of old tiles to replace handy, and check it afterwards so it doesn't, you don't have leaks. If you're on a flat system, a flat roof, you're likely to pay $500 more for the tilt system. And this one is important. Check system size limits with asset owners. One of the issues at the moment for the asset owners is that with all the solar systems that are going in, they can get too much power being produced in the middle of the day, and they've had to limit output. And in some places, you're not allowed to output, or you're only allowed to output up to a 5 kilowatt system. So that will give you a maximum system size that you're allowed on your house. If you do have a 3-phase system to your house, though, if you're on 3-phase power, typically they'll let you do that 5 kilowatt limit to each phase. So you can have up to 15 kilowatts normally, and sometimes up to 30 kilowatts. I won't talk about this too much because I have done a post on it and I'm aware of time. Only to say that you're making all of your power, a lot of power in the middle of the day now. Start thinking to yourself, or educating your owners to think of their house a little bit like a battery. You're making this power in the middle of the day. What can you use it on? Well, let's shunt it to that heat pump hot water. Let's put it in there. Okay, the hot water's hot. Now what can we do with it? Okay, let's put on the heating. To heat the home or cool the home in summer. When the sun goes down, turn it off, and our great insulation that we talked about in the first webinar will hold that heat within the house. And also, the future is very close. We're doing a project, our next project, we're hoping to incorporate this, and that is an electric car. Electric cars are actually battery packs on wheels. And this is what's coming, something called V2H, which is vehicle to home, or V2G, vehicle to grid. not quite sure which naming convention is going to win out there, but keep an eye on that, because it was a technology where the power from your house, when your car's plugged in, you can put it into your car, and potentially you can run your house off your car and use that. And that way you don't necessarily potentially need to have big battery packs as well on your home. Your car will be your battery pack. And just to be ready for this future, I would suggest everyone, here's a low-hanging fruit, put in a 32 amp cable that runs from your meter box to wherever you think the car charger is likely to be. Ask the owner where they want it, and just leave it in the wall for that time when they get an electric car. And in your meter box, leave 2 free circuit spots at least, so that they can connect up that circuit, and the 32 amp will give you fast charge capability. So you've offset with photovoltaics. Well done. You should be very close now to carbon neutral, potentially carbon positive over the year. Here's one idea. If you're not quite there, the amount of energy that this house will be drawing from the grid won't be substantial. And if owners are disappointed at all that they're not 100% carbon neutral, just tell them to get pay the 5 cent extra premium for a kilowatt per for green power, and effectively for what won't cost them very much because they're not using much power, that would take away any shortfall from this rule of thumb sort of system, and effectively mean that their carbon footprint is pretty much gone. So well done, high performance living. And I guess what I was trying to do in this webinar and on this series is really give a message of hope for our industry, to say that all the technology that we need is actually already here. It's just a matter of applying it. And these aren't hard things to do. It's just a matter of just maybe incorporating 1 or 2 new ideas in each time you build. 3 or 4 homes later, you too could be a builder who's building very energy efficient homes and being raved about by your clients. So that's it. You might notice here, minimize embodied energy is also on this roadmap. We will get to that sometime down the track. All right, everyone. The road is open. Time to drive. Back to you, Hamish.
Thanks, buddy. Very, very informative. I know you could have kept talking for hours upon hours. A very, very knowledgeable man. Thank you very much for that. We'll try and get through a few of these questions. I know we're pushing close to 6 o'clock, but hopefully we can get through these questions. Everyone can hang around for a couple more minutes. Jeremy, if you had an old heat pump that you want to reuse, how can you check if it is efficient enough or only runs on 100% and not worth keeping? I think that relates to a comment you made earlier on in the presentation.
So really the only way is to look up on the internet and try and find the product manual, and the product manual will hopefully have the specification for the system. If it's such an old system that you can't find the product manual, or the product manual doesn't even mention how much power it uses, it's probably a good time to change it over. Just be careful again of making sure it's decommissioned properly.
Yeah, it's a shame that we still live in this sort of waste.
Yeah, I know. I hate it too. I hate throwing stuff out at the at least these things are mostly made of metal, and they can be so they will be recycled. Yeah. So you can sleep a little bit easier. But. Yeah,
unfortunately, sometimes the cost to reinstall them does outweigh the benefit of reusing them. But anyway, it's probably a topic. In fact, it's something we'll get to at the end of this for our next webinar. But anyway. This is one from Paul, and this is probably a bit arbitrary, and we may or may not be able to answer this question because it does depend on a few factors. But what is the best air tightness you can be expected to achieve with a design that uses plaster as its airtight layer?
Okay, so this is a topic of conversation at the moment. Look, I just had a blower door test, and my air tightness was 5.2. on that particular job. I had another one a little while ago, and it was just over 5 as well. And that's really speaking to one of our other sustainable builders. You know, I wouldn't want to go much tighter than that without some sort of heat recovery ventilation. And I could, if I wanted to, go tighter than that. I know a few places where air is coming in. And that's one of the lovely things about actually doing the blower door tests. And I'd suggest, it doesn't matter if you're a passive house builder or you're a standard builder, you should be doing blower door tests just to know how tight you're actually building, because there's also that risk that if you say, I'm going to go as tight as possible and cork up everything, if you go to the nth degree, you may very well have a house that is so tight that it really should have had a heat recovery ventilation, and you'll get stuffiness problems. So, and potential health effects. So a good question. But speaking to the blower door tester on the day, he was of the opinion that he had never rated anything that had got below 3 air changes, which is sort of the technical, everyone says below here, don't go without a heat recovery ventilation. So there might be
full disclaimer there though. We don't have the data to back that up. It's sort of an arbitrary.
This is all my opinion and just what I've read, and it's still a work in progress, I think, for the whole industry on what is a good level. Thanks, Hamish.
No, that's right. So, and just a quick comment on the air exchange or blower door test too. You know, we're passive house builders, and we do 2 tests, and one pre-plaster and one after plaster as well. So, look, that's probably another topic all in itself, and we could totally get sidetracked down there. But
that's partly the benefit of being a passive house builder, is you've got that membrane on the outside, so you can do it. It's not going to mean much for a conventional builder if you do the blower door test before the plaster's up.
Yep, absolutely. So Rhiannon did ask, what is the Facebook group, which you did touch on, but thank you. So there is a Builders Declare Australia Facebook page, but we also have a Builders Declare group. So please join in and join that group and ask the questions. We do want to grow that. We want that to be a hub to start a conversation so we can share ideas, experiences, products, and all that kind of stuff. Really excited about to grow that group. So please join that one. Here's another question from Brian. Can you please discuss the costs associated with heat pumps versus a conventional hot water system? For example, a standard Stiebel Eltron hot water heat pump at $2,800. Whether or not that's Australia-wide prices, I don't know, versus a standard hot water heater, either gas or electric.
I'd say there's $2,000 in it. Well, no, maybe not. Okay, so if I was doing no, that's wrong. A normal hottie on the wall, if I was getting a 6-star or a 7-star instantaneous gas system, I'm probably looking at about 1,100 or so for the actual unit, and then plumber on top of that. So it's maybe 1,500, 1,600 installed, something like that. Versus that price for the Stiebel Eltron. I'm not actually 100% sure. I often use a different brand, but yeah, I'd say maybe it's the same plus plumber. So what are we looking at? I'm trying to work out in my head. My head's gone to jelly. It might be $1,500, something like that difference.
Yeah. So I mean, our experience as well, because we do heat pumps as well. And look, just for the record, there are a number of different heat pumps out there. Look, in our experience, you're looking at $1,500 to $2,000, but then your savings are over the life of that product. But also and just check out the rebates that you can get installing heat pumps too.
Yeah, it's the other nice thing that I really like for the client is if the house does go to this whole electric thing, they only have one bill. They've got one bill and they've got one figure, so they know how energy efficient their home is. But if you've got megajoules and you've got kilowatt hours, who does that calculation to work out how much energy they're using? It's hard.
Yeah, well, I guess that's why they're listening to these webinars.
Yeah, hopefully.
More information. Here's another question. Can you please clarify the expectations on heating and cooling or parameters so we have some kind of idea of the expectations at 6 star? So basically high and low temperatures and also max and min temperatures, please. So,
okay. So the house energy rating software itself, I would have to pull up to know them off the top of my head. It is something like in the living spaces, it assumes while you're in there, temperature of about 20 degrees. I think it assumes the air conditioners go on at 24 and that heaters go on at 19. Don't quote me on that. It's something like that. And it also assumes things like the windows get opened if it's cooler outside and you're hot inside. So there's definitely some assumptions that the software makes about how one lives in the home. It assumes blinds will be pulled down if too much heat is coming in summer. And that may not be the case if you're there. So I think it's important to let owners know that I actually, if you had warned me, I would have had those in front of me because my handover manual goes through all that. I just haven't learned it exact off the top of my head. I also know that bedrooms have a lower heat profile because they assume at nighttime it doesn't need to be as warm in bedrooms because people, are under the covers. So there are some assumptions there, but the examples that I gave of the energy use of existing homes, that is, people living in the homes using sort of the NatHERS software to try and get a good performing house. So while there are issues, there's definitely still value in the NatHERS protocol, at least from my point of view.
There's another couple of things to get through here. So there is a question here, which whether or not we want to go and start naming brands or align ourselves specifically with brands, but there is a question that asks brands for air conditioning, air cons, what would be the best?
Well, I think I mentioned the US 7, so I may as well.
The Daikin.
I'll say Daikin. But no, I wouldn't say that's necessarily the best. It's just, look, that's just the one I've used the most recently. But to tell you the truth, I've used Fujitsu's, I've used LG's, and I've used Mitsubishi Electrics, and I haven't had issues with any of them. So, they're so ubiquitous around the world. I think they've had their testing phase. I think you can trust them.
But let's not also forget our sponsors for this evening. Steve Eltron also have a bunch of great products, so definitely check them out. Look, we might wrap it up. Yeah. We might wrap it up there, Jeremy, because we are past 6 o'clock. So thanks everybody for joining us, and thank you, Jeremy, for your presentation. Another big thanks to Steve Eltron. Again, if you'd like to know more about their products and their range, check out their website. Again, that's www.steeble-eltron.com.au. Now, our next webinar, which I'm particularly excited about, and it's titled Renovate or Detonate. It's going to be a roundtable discussion between some of our founding members on whether to renovate existing homes or build stock, or bulldoze and start again. So this is something that we've been talking around with some of our founding members of which way we would go, and there are definitely some pros and cons to both. So look, I'm not going to say we're going to solve all the problems or come to a definitive answer, because I think it is a case by case, but it's certainly going to be a really interesting topic. But I'd love to throw it out to any of the viewers tonight to see if they've got any thoughts on this topic. Now, there's no right or wrong answer, but please get in touch with us on Instagram, Facebook, or email. Our email address is info@buildersdeclare.com. You can also just join the discussion on our Facebook page and our Instagram page. There are a couple of other little questions coming in here, which I might pass for today, but again, thanks everybody for getting involved. And yeah, Jeremy, thanks again. And thanks everybody for listening.
Thanks, Hamish. Thanks, everyone.
Okay.